this video is going to be all about polymerization. In this video, we're going to learn what a polymer is. Then we're going to distinguish between natural and synthetic polymers or man-made polymers. We're going to distinguish between addition polymerization and condensation polymerization, and learn how to identify the empirical formula of various polymers, polyalkenes, which are formed by addition polymerization, and also polymers that are formed by condensation polymerization. You'll also name and identify the different linkages in the different polymers. For instance, you'll learn how to name and identify the linkage in a polyalkene, which is going to be an alkane linkage. And you'll name and identify the linkages in all the rest polymers that are formed by condensation polymerization as well. Finally, by the end of this video, you should know some uses of the different polymers and how they impact the environment and living systems, meaning humans, animals, plants. Polymerization is really the making of polymers. Polymerization is going to be linking together of smaller molecules. So let's say we have this small molecule here called a monomer, because it's just one small thing. So we have monomer, and if we link a bunch of these monomers together into a chain, then we have a polymer, because it's poly, many monomers. Yes? Polymerization is really the linking together of many monomers or small molecules to make a larger molecule called a polymer. So a large macromolecule. It's a macro because it's large. We see that polymerization is really just the making of polymers. It's linking together many monomers to make a larger macromolecule called a polymer. So polymers are just large molecules or macromolecules, and they're just long chains of small molecules known as monomers. So the monomer would be one, and the long chain linked together is the polymer. We need polymerization to make these large molecules because the large molecules will have different useful properties than what the monomer might have. Okay, so why is polymerization important? Polymerization is important so that we can make these large molecules or polymers that will have different useful properties. Now, they have different properties from the monomer, and the different properties make them beneficial to a living system. So a good example is going to be glucose. Glucose is a simple sugar or a monosaccharide. Mono meaning one, saccharide sugar. So glucose is a monosaccharide, right? And so glucose gets absorbed into our bodies to make energy. That's our monomer. Our monomer gets absorbed into our bodies to make energy. But what do we do with the glucose when we don't need energy? Like, well, you eat dinner and you don't need the energy right now because you're going to bed. You don't need energy to go to bed. Or you don't need energy when you're going to go sit and watch a movie for 2 hours, but you're eating popcorn. Instead of making all this energy and not using it, we link up all our monomers, all our glucose monomers. We link them up together and make a polymer. So in humans and animals, we eaten all this sugar, all this food, whatever, and now we have glucose being absorbed into our bodies, but we don't need the energy right away. We link up all the glucose to make a polymer, a polysaccharide to be exact, because we linked up a bunch of monosaccharides. Now we have many sugars together. We have a polysaccharide, and we call this polysaccharide glycogen. Once we link up all these glucose molecules together and we make glycogen, we can store it in our liver for whenever we need it next, because glycogen is less reactive than glucose, and so it can be stored for later. It's not going to do anything. It's just going to stay there, and when we need the glucose for energy, we can take it back out, change it back into glucose, and get our energy. Plants also, when plants do photosynthesis, they make glucose. But how much energy do you think a plant really needs? It's not moving, it's not running around, it's not going anywhere. So instead, it's going to make a polymer. It's going to take all those glucose molecules that it made in photosynthesis, link them up together, and they can make two different polysaccharides, I should say, because they're linking up a bunch of monosaccharides. So they can make two polysaccharides. They can make cellulose, which is going to be used to make their cell walls. So now they've made strong and sturdy cell walls to protect its cells, which we know is even more important because they can't run away. So it's important for them to be strong, and they need to grow upwards, defying gravity. So cellulose is going to be important. And how is that made? It's made from linking together a bunch of monosaccharides, making a polysaccharide. And it has different properties. It's stronger. Glucose, sugar just melts away in our mouths. But cellulose is very strong. Also, plants, if they have a bunch of extra glucose, some plants will make a polymer called starch, will make a polysaccharide called starch that's also less reactive, just like what humans were doing. They're doing it as well. It's less reactive, and so they can store it. And then they store it in different places. They store it in their roots. They can store it different places. And then, lucky for us, if they store a bunch of that polysaccharide somewhere, example in their roots, we can get a potato. And we get to eat it. All that starch. Another good example of the importance of polymerization is to make proteins. So our bodies absorb amino acids. They absorb simple amino acids. That's going to be our monomer. Once the amino acids are in our body, they can be linked up together to make proteins. So linking up a bunch of amino acids is going to make a polyamide. The amide coming from the amino. Or what we know it as is proteins. So a bunch of amino acids linked together makes a protein. And why do we need these proteins? We need proteins to grow and repair ourselves. When we need to grow, we need to make new body cells. That's the protein doing that. We need to grow hair, nails, anything thinking about growth, it's proteins. All hormones are proteins that send the messages all around our bodies to tell us, okay, we need to sleep now. Okay, it's that time of the month for us girls. And proteins are also enzymes. Enzymes are proteins that break down food into monomers so that we can absorb them into our bodies. And once we absorb these monomers, we can link them up to make whatever polymers we need in our bodies. So now we're going to distinguish between natural and synthetic polymers. So far we've already discussed our natural polymers, which were proteins or polyamides that were made from amino acids, and polysaccharides, which are made from a bunch of monosaccharides or sugars like glucose or fructose or galactose. The polysaccharides that we discussed were glycogen, cellulose, and starch. And here next to my natural sign, I have a little potato just to remind you about that. Our synthetic polymers, or our man-made polymers. Number one, our most famous synthetic polymer, plastics or polyalkenes. From this name, we know that it's many alkenes joined together. Alkenes being our organic molecule with double bonds, right? And so we have plastics, and up here I have some of the plastics. You have plastic bags, bottles, PVC pipes, those big white plastic pipes that run in our houses and gutters and things. And non-stick pans. This is supposed to be a non-stick pan, that's why it's black. Non-stick pans, that's also plastic. And then we have nylon, which we use to make our fishing lines or seat belts, any stretchy things like exercise clothes. And we have polyester, and we mostly see polyesters in clothes. Also, PET water bottles are also polyester. But clothes, if your clothes say 100% polyester, it's basically saying 100% man-made. We just don't know that, and then you think because it says 100% that it's a good thing, but it's really 100% synthetic, so something to think about. We have a little shirt here for clothes, the synthetic things. Another difference between our natural and synthetic polymers are that our natural polymers are biodegradable. That means they're going to decay if you leave them outside. That's why we can throw our banana peels out the windows and our chicken bones and such things. However, our synthetic polymers are non-biodegradable. So if you leave them outside, if you throw them out the window, they're going to stay there. They're going to persist for a very, very long time. And then it'll be called pollution at that point. So litter, all these different types of pollution. And then if they get into our seas and our waterways, what's happening is our turtles and our fish and our marine life are mistaking plastic bags and bottles and the different things for food. And they eat them and die, they choke. Or they are being suffocated by the plastics. right? So it's killing our marine life, especially killing animals, but especially our marine life. And then the other bad thing about our synthetic polymers, especially plastics, are that they're flammable. And not only are they flammable, but when they burn, they let off a lot of air pollution, a lot of soot, a lot of dark black smoke, which means that we can't leave them outside to rot, so we can't get rid of them that way. And we can't get rid of them by burning them. So we really have a problem with making too many synthetic polymers, because how do we get rid of them? This is where our green people come in with the recycling and the reusing. So how do we make these polymers? So we're going to start off with making our synthetic polymers first, because we're humans and humans are the ones that make these. So we're going to start off with making our synthetic polymers. And we know our synthetic polymers are plastics, nylon, and polyester. So we're going to start with our plastics. Our plastics are actually polyalkenes. That means they're made of many alkenes. And these plastics are made using addition polymerization. So that's the type of polymerization you use to make plastic. Addition polymerization. And addition polymerization is where many identical alkenes are linked together. So the monomer here is going to be your alkene. That's your organic molecule with a double bond. So alkenes are going to be linked together. And also need to note that for addition polymerization, you require high pressure, a catalyst, and heat. So whenever you do an addition polymerization, your special conditions that will go on your arrow are going to be high pressure, a catalyst, and heat. So it's a lot of work for us to get to make polymers for ourselves as humans. Okay, we need high pressure, a catalyst, and heat. And we're going to be adding together some identical alkenes. So how addition polymerization happens is that the alkenes, the monomers, are going to lose their double bond and form an alkane linkage. Okay, so they're going to link together by losing their double bond. So I drew a little diagram here. So they're all identical, as you can see. They have the same hairstyle. And so these two are in a double bond. So they're holding their both hands together. So it's a double bond. They're bonded two times. They're bonded with their left hands. They're bonded with their right hands. And these ones, same thing. So these are two identical alkenes, two identical molecules that have a double bond. Now, if we want to link them together, we want to link these monomers together to make a polymer, because remember, a polymer is a chain of monomers. What's going to happen is they're just going to release one hand, and then they can hold hands with the other molecules. So if both molecules release one hand, break that double bond and make single bonds, then they can all just hold hands together, and this is going to be our polymer, our chain. That's how addition polymerization occurs. And the link between the two, so these are the two molecules, the link between them, here is where they get linked together, is called an alkane linkage, because it's now saturated. It now looks like an alkane. It has single bonds. Okay? Now we're going to go look at some actual alkenes bonding together now, and some different plastics that we can make. Our first plastic is going to be polyethylene. So the name basically tells you exactly what's going on. It's many, poly means many ethene molecules. So that's an alkene, so we know that this is addition polymerization, because that's the one that joins alkenes together. So we're joining several ethene molecules together to make polyethylene. Polyethylene is important to make. Why do we need to figure out how to make polyethylene? It's because polyethylene is what we use to make our plastic bags. That means also like any packages, like your chips bags and all the snacks, the bags, and your cling wrap, your saran wrap that you use to cover things down. That's going to be all polyethylene. So we need to figure out how to make it. And we know it's by joining together ethenes. So we have an ethene molecule. It's means 2, so it has 2 carbons. And double bond because it's an alkene. So we have ethene and another ethene, and they need to join together. Remember, there's a special condition, high pressure, catalyst, and heat. And then they'll join together by just releasing that bond, just like the image we saw before. They'll each break their double bond, and their fourth bond will now instead be between each other. So they'll become this, 1, 2, 3, 4. And now this single bond, where it used to be a double bond here, now is a single bond with the other molecule. What used to be a double bond here is a single bond with the other molecule. Okay, and then that will happen a bunch of times, and that's how we'll make polyethylene. When you write these reactions, you'll see they have a little N in front. That's because it's not just going to be one ethene joining with another ethene. Normally, polymers have 50 or more monomers joined together. So we put N to mean many, or any number of ethene, and this unit is going to keep repeating, so we put N here for how much ever times we need it to repeat. So your empirical formula is really a smallest repeating unit that you can show to demonstrate the molecule, the smallest repeating unit that if we repeat it a bunch of times, then we'll get the actual molecule that we're talking about. So our empirical formula for polyethylene is going to be just 2 carbons and H's, because that's just repeating over and over and over and over, and then we can get our polymer. Okay, so that's our first plastic that we just learned how to make, was polyethylene, and that makes plastic bags, packagings, cling wrap. Okay, the next plastic we're going to look at is called polychloroethylene. Poly, many. So once you cut off the poly off the word, you figure out what the monomer is. So if we take out poly, then we'll figure out that the monomer that's repeating is chloroethene. So it's just an ethene with a chlorine attached. And we know we're going to have N's in front of here to show that it's many chloroethenes, right? So polychloroethene is really our PVC. So the C in PVC is actually coming from that chlorine that's on our ethene, okay? So PVC, you know how PVC pipes, those big white pipes that fit together, like the water pipes in homes, gutters, like when you can even use polychloroethene, PVC, to make plastic windows and things of that nature. Now, how do we make it? We're going to add a chloroethene, so just an ethene with a chlorine instead of a hydrogen up here, to another one. So in addition polymerization, remember, it has to be adding identical monomers, identical alkene monomers. So when we join these up together, this one's going to release its double bond to join to this one. This one's going to release its double bond to join to this one. And you'll see where the link happens, it's not the 2 chlorines together. Instead, it's going to be where the chlorine and the hydrogen are together. So when you draw out your polychloroethene or your PVC, you're going to have your 4 carbons, yes. But what you're going to see at the top is going to be HCl, H then Cl, H then Cl, repeating pattern that way. Okay? So be careful of that. At the bottom is just hydrogens, so that's why I'm not talking about that. Then empirical formula is going to be, what's the smallest unit that keeps repeating? It's going to be 2 C's, H, and that 1 Cl there. That's going to just keep repeating. That's PVC. The next plastic we're going to make is polypropene. So remember, we just take the poly off to figure out what the monomer is. The monomer in this case is propene. So propene, prop tells us there's 3 carbons. So 1, 2, 3 carbons. The reason we're going to write it this way is because we know that the bond has to happen between the carbons that have the double bonds. So that other 3rd carbon that has a single bond is not the area where the bonding is going to happen. So we just put it up here in its condensed form, CH3, instead of doing the C and drawing the 3 H's around it. We're just going to write CH3. Okay? So we have many propenes. So propene, 1, 2, 3 C's. This is how propene is going to look, though. You're going to set it up like an ethene, and we're going to add 1 more methyl group up here to make the 3rd carbon. When they add together, the addition is going to be between the carbons that have the double bonds. And we're going to get an alkane linkage between, we already know that because addition polymerization or making polyalkenes ends with an alkane linkage. That's the type of linkage. Okay, so we need high pressure, catalyst, and heat, and they're going to all link together, and the repeating is going to happen similar to the PVC. You're going to have this time H, and then a methyl group, H, and then a methyl group. And that's how it's going to repeat, meaning the empirical formula is going to look like C with 3 H's, but a methyl group up here instead. Don't forget your N to say that it's going to be many of these. We forgot to say what polypropene does. So polypropene is the plastic that we use to make ropes and plastic toys, carpets. How do I remember polypropene? It kind of sounds like rope is in there. Actually, rope is in there. R-O-P-E is in there. Polypropene makes ropes. And then you have to just remember the toys and the carpets, really and truly. All right, our next one is polystyrene, and the word that we use to refer to polystyrene normally is styrofoam. So that's the next plastic we're going to learn how to make with addition polymerization. So polystyrene or styrofoam, we already know automatically, once you see polystyrene or styrofoam, you should know what its uses are. It's used to make food containers, especially fast food containers. You're gonna have cups and protective packaging material. You know, when you order things and they come in boxes, there's normally a bunch of styrofoam in there to protect whatever you ordered. And also insulation in walls and roofs, because we tend to have our roofs are metal. So if the sun is beating like it is right now in Antigua, then inside of your homes would be very hot if we just use the metal roof. But we have insulation. That's our styrofoam to stop the conduction of that heat, right? That's our styrofoam uses. Let's get right into it. How is styrene gonna look? Because we know our monomer is styrene, right? We take off the poly, we figure out our monomer. Our monomer is styrene. Styrene looks like this. You have your two C's and your H's as usual. And this group at the top now is going to be C6H5. C6H5, okay? So styrene plus another styrene. Remember, it's many styrene and many styrene. And we need high pressure, catalyst, and heat for us to do these man-made things. And then we're going to get an alkane linkage. So it's going to become single bonds instead. And we'll see an alternating pattern at the top. H, C6H5. H, C6H5, right? And that's our polystyrene. Our empirical formula is going to be our 3 H's and our 2 C's, and then our C6H5 up there. Don't forget the N to say that it can repeat. It can repeat several times. We have one more plastic to learn, and it's called polytetrafluoroethene. It's a very long name. PTFE for short. Polytetrafluoroethene. Let's break it down. So we already know that if we take off the word poly, then we'll figure out what our monomer is. So our monomer is tetrafluoroethene. That means 4 fluorines on an ethene, pretty much. Tetra means 4. Fluoro is fluorines. Ethene tells us there's 2 carbons, eth for 2, and a double bond. So it's literally telling us how a monomer looks. So our monomer is 2 carbons with a double bond. That's our ethene. And 4 fluorines, so F's all around. No H's this time. So many tetrafluorines, if we join them together, what we get is going to be alkane linkage, so single bonds, and all fluorines, fluorines across the top, fluorines across the bottom. That is PTFE, polytetrafluoroethene. Our empirical formula is just going to be 2 carbons and fluorines all around, single bonds. Don't forget your N's to say it's many. And what is PTFE used for? PTFE is the plastic that's used to make the non-stick coats. So when you coat your frying pans and your pots, your non-stick pans, your non-stick kitchen utensils, and your non-stick garden utensils, those are made from polytetrafluoroethene. That's PTFE. All right, so just quick, let's go over what we just learned. We just learned that plastics or polyalkenes are made by addition polymerization of identical alkene monomers, okay? And when they join together, the linkage is an alkane linkage because they get single bonds instead. We went through 5 examples. We went to our regular polyethylene that was used to make our plastic bags. And then we did polychloroethene, which is our PVC, the C for chloro. Polychloroethene, which is our PVC pipes and such things. And then we went through our polypropene and polystyrene. Those are the 2 that have methyl groups as their top corner. So in our polypropene, which is used to make ropes, we had the CH3 at the top corner. And in our polystyrene, which is used to make styrofoam, we have our C6H5 up in the corner. And then finally we did polytetrafluoroethene or PTFE, which is all fluorines surrounding to make our non-stick coats, right? Now, all our rest polymers, so everything except our plastics, are going to be made by condensation polymerization. Plastics, addition polymerization. Everybody else, our natural polymers and our nylon and our polyester, are going to be made from condensation polymerization. Okay, so let's move on to condensation polymerization. So far we already know our polyalkenes or our plastics were made by addition polymerization. That means all our remaining polymers are made from condensation polymerization. That means all our natural polymers, so proteins and polysaccharides, and our 2 remaining synthetic polymers, polyester and nylon, are made from condensation polymerization. Polyester is for the shirts, nylon for the fishing line, and our favorite starch, potatoes, for our polysaccharides, right? So let's get into it. Condensation polymerization is the linking together of two different monomers by removing a water molecule from between them. So that means one monomer will give up a hydrogen and the other monomer would give up a hydroxyl group, and together that H and that OH will make a water. Okay, so here's our example. This time our monomer has both its hands full, but not because it's making a double bond, but because it has a hydroxyl group in one hand and it's bonded to its other carbon in the other hand. And this monomer has a hydrogen in one hand and it's bonded to its other carbon in the other hand. Notice how they look different, because in condensation polymerization, you can bond together two different monomers. So this monomer has this hairstyle. This monomer looks a little different, to show you that two different monomers can join together. And to join together, they're going to give up, one will give up an OH and one will give up an H to make a water molecule. And now that this hand is empty, now there's no hydroxyl in this hand and there's no hydrogen in this hand, they can now hold hands and make a bond together. And that will be the link in our condensation polymerization. So condensation polymerization, they bond together by losing a hydroxyl and a hydrogen. So they basically lose a water molecule and then they link together. And where those two molecules join will be the linkage. So we're going to start off with our condensation polymerization of our synthetic polymers, the ones that are man-made. So for synthetic polymers, although condensation polymerization is the addition of two different monomers, when you're making synthetic polymers, each monomer must have its two ending functional groups matching. That means when you're making the synthetic polymers, our first monomer must have the same functional group on both sides, and the second monomer must also have the same functional group on both sides. I think when you see it, it will make more sense. So for polyester, that's our synthetic polymer that's made from condensation polymerization. For polyester, we have two different monomers. We have a dialcohol and a diacid. To make our synthetic polymers, we have to have these di molecules. So the alcohol, no matter how much carbons are in here, so I just put an X to represent how much ever carbons. At the two ends, they must have the same functional group. And since it's an alcohol, we know our functional group is our hydroxyl group. Yes? So for polyester, we have a dialcohol and a diacid. So whatever the carbons and then our functional groups. Actually, let's go over our functional groups really quickly just in case we don't remember them. So functional groups. A hydroxyl group is OH and that's identified as an alcohol. A carboxyl group or carboxylic acid group identifies a carboxylic acid and it'll be C-O-OH. On this side where I have nothing means that's where it'll bond to the other carbons. An ester group has C-O to an O. Okay? C-O to a O, not an OH. If there's a C-O and an OH, it's carboxyl. Ester, the C is bonded to two just O's. One is a double bond, one is a single bond. And this is a new functional group that we're now being introduced to, which is the amine group or amine group, however you want to say it. And it's a nitrogen bonded to two hydrogens. Now, nitrogen can only make 3 bonds. So we know carbons make 4 bonds, but nitrogens make 3 bonds. That's why it's bonded to 2 hydrogens. Oxygens make 2 bonds, so you'll notice that this oxygen has 2 bonds, so it's full. Moving on. So all I want you to understand is that for condensation polymerization, yes, it is 2 different monomers joining together. But if you're making your synthetic polymers, those monomers have to be di molecules. That means their 2 ends of their molecule have to have the same functional group. Okay? Now let's just get straight into it. So polyester, it's doing condensation polymerization. So that means this guy is going to give up his H and this guy is giving up an OH, and they give them up and they'll make water. Now, this oxygen has a free hand now, because the hand that it was using to hold on to hydrogen, it now has free to bond to carbon. And same thing over here, carbon now has a free hand because the hand it was holding on to the OH is now free to make a link here with the oxygen. And so Altogether now it's going to look like this. And the link between them is an ester linkage. See, it's the same as the ester group. It has a carbon to two, double bonded to O, and to another, and a single bond to another O. So it's an ester linkage. So polyester is called polyester, not because the monomer is esters, but because once it's made, it's going to have a lot of ester linkages. So that's why it's called polyester. And it's easy to remember your monomers for polyester because we know an ester is made from combining an alcohol and a carboxylic acid. So to make a polymer, we need a dialcohol and a diacid. And this is going to be our polyester. Now, one way that I remember that polyester is made from condensation polymerization is because of ester in the Bible. So how is ester in the Bible help me to remember that polyester is made from a condensation reaction? Because Esther, she really needs something in the Bible. She really needs a certain outcome. And so she decides to fast, and she gives up not just food, but she also gives up drink. That means she gives up even down to water. So there's lots of fasts in the Bible. You can fast from different things, but most fasts would still include drinking water. But an Esther fast gives up water, and so making a polyester, you have to give up water. And not only did Esther have to give up water, but she asked all the Jews to also fast and give up water as well. And then she did her fasting. After the fast was over, she did indeed achieve what she wanted, and the Jews became an even stronger people. They were given so much power after this. So essentially, if you can remember that story, you should also be able to remember condensation polymerization, because to join together and become a stronger thing, they have to give up water. They had to fast from water. So they gave up water, and then they came together and they were stronger for it. So that's my little mnemonic, I guess you could say, a way to remember that polyester is made from a condensation reaction, and condensation reactions require the giving up of water, the removal of water to join together. So in condensation polymerization, what you'll see for sure is that they'll have two products at the end, your polymer and water. And our other synthetic polymer that's made from condensation polymerization is nylon. Nylon, we know, is used to make fishing lines, nylon stockings, seat belts, anything really stretchy, you'll think nylon. Now, the monomers to make nylon, since it's a synthetic polymer, we know the monomers have to have di molecules. They have to have the same functional groups at the end. So whatever the carbons, whatever, it doesn't matter. To make nylon, you need to have a diacid and a diamine. That's our new functional group here. So whatever the carbons, you need a carboxyl group at the two ends, and you need a diamine, which is whatever the carbons, you need amine groups at the two ends, which is an N and two H's. Okay, so this is just to show you that condensation polymerization, you're going to get water in the end, and also to show you that when you're making the synthetic polymers, polyester and nylon, using condensation polymerization, they have to use di molecules. It's two different molecules, yes, but they had to both be di molecules, meaning their ends are the same. Okay, oh, and nylon, because the monomers for nylon is an acid and an amine, that's why we got the name polyamide, okay, because of the amine in nylon. And you can remember because nylon begins with N, so that's a little hint to say that, hey, you need N's to make it, okay? Let's look a little deeper into the nylon. So nylon, you're using a diacid and a diamine. We already know that. This is going to give up its hydroxyl. This is giving up its H. It has two H's. We're just going to give up this H because on CXC, that's the H that they're going to give up as well. So they're going to give those up. That's water. And then they're going to, now that carbon has that free hand, and nitrogen have a free hand, they can hold hands together. The C and the N will bond together. And this is going to be your polymer. You're going to have C double bond O, how much ever carbon, C double bond O, and it's going to be bonded to an N, left back with an H, and we have our carbons, N, left back with an H. You'll see that the empirical formula for synthetic polymers formed by condensation polymerization will have a double repeating pattern because of those di molecules. You'll see a double repeating pattern. So we'll see the C, then the C, then the N, then the N, then the C, then the C, then the N, then the N, then the C, then the C, then the N, then the N. When we're making the polyester, we will see the O and O, C, C, O, O, C, C, O, O, C, C, because of the dialcohol and the diacid. The point is you should see this double repeating pattern. Same, 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 same. Once you see that happening, you'll know that it was a synthetic polymer that was made because of that. Okay? And we'll see why that is later down. Let's get into condensation polymerization of our natural polymers. And yes, I have my potato once again to remind you about starch being a polymer. Now, in condensation polymerization of natural polymers, the two different monomers that are used to make natural polymers do not need to have the same functional group on either side. That means that the monomer can have a carboxylic acid group on one end and an amine group on the other end. They do not need to be di molecules. Why is that? It's because God made our bodies to be able to order things even at a chemical level. So what I mean is, to make proteins, your monomers are amino acids, right? So an amino acid is set up such that on one side they have an amine group and on the other side they have an acid group. Yes? Now, humans, we can't synthesize our synthetic polymers using molecules that have two different ends, because to make this amide linkage, we need the carboxyl group to always react and meet with the amine group. But if we as humans try to do this, how can we ensure that every time that they meet in this exact orientation? Because sometimes this carboxylic acid might meet with this carboxylic acid and we'll never get as long of a chain as we want. So even if we get about 3 of them to meet at the same one, how do we ensure that the next one is flipped the correct way to bond with the other one? I don't know if you understand what I'm saying, but the point is that if we have 2 different functional groups, we'd have to ensure that the 2 that we want to react always meet every time, and we haven't figured out how to do that at such a small chemical level, but God has, and our bodies know how to do that. So our bodies can take an amino acid and make sure that the next amino acid that joins to it bases its amine group to the carboxyl group, and we can make so many different proteins. Well, not us, our bodies that God designed. So let's just get into the details. Some examples of proteins that we know are enzymes, and those are used to break down things into smaller molecules. We have hormones that send messages and trigger reactions in our bodies. We have growing our cells, repairing our cells. Anything that grows a lot, we know that means there's protein doing all that work. Okay, and our monomer is amino acid. This is how amino acids appear. They have an amine group bonded to a C, and on that same C there's also an acid group, which is why the name is amino acid. You have a C in the middle and you have amino acid, right? What makes all the different amino acids unique or different from each other is what is the 4th thing bonded to this carbon. So this carbon will be bonded to amino acid and a hydrogen, and then the 4th thing bonded to it can be pretty much any alkyl group. We could have a group with a chain of 10 carbons, we could have a chain of 3 carbons, we could have a ring of carbons, different things. So this group down here represents just whatever amount of carbons and stuff it'll be added to. So our amino acids will look like this. You have the amino acid proof, and then they have little tails, different tails. They have different R tails, we'll say. Now let's just get into the bonding. So the acid is going to give up the hydroxyl because the nitrogen only has a hydrogen to give up. So they're going to give them up and make a water molecule. And the now free hand of this carbon is going to hold the free hand of this nitrogen. And they'll come together. And this is how our final protein is going to look. It's going to be, this is the linkage, the amide linkage, where they linked hands. C double bond O to an NH. And it's an amide linkage, which is the same linkage that we saw in our nylon. The only thing is that if we look at this with our nylon, we had a double repeating pattern because we had a diacid and a diamine. So we saw NNCC, NNCC. But instead now we're seeing NCC, NCC. It's not just doubles that are repeating. So that's how you'll know that it's a protein versus if it's nylon when there's an amide linkage. Also in proteins, the amide linkage is sometimes called a peptide linkage, okay, because it's proteins. And now our final polymer is a natural polymer that's made from condensation reactions, as all our natural polymers that we know are, and it's polysaccharides. Polysaccharides, the examples that we know are starch, when plants decide to store up their glucose. We have cellulose, if we try to make plant cell walls, and we have glycogen. If us as humans are storing up our glucose, we store it as glycogen. All right, so our monomer polysaccharides are going to be sugars, any monosaccharides. That means it could be glucose, fructose, or galactose. For the purposes of CXC, we're just going to use glucose. This is how a glucose molecule looks. It's quite complex, and yes, it matters which direction the OHs go, which ones the H's go. Like these two OHs have to be on opposite sides and all these things, and you'll learn that in the future, but lucky for you, you do not need to know that right now. I'm just showing you this so that you can understand why we just reduced glucose down to an X or a R, whatever letter to represent carbons and hydroxyl groups. It's because the bonding together or the linking together of the different glucose molecules is going to be using the hydroxyl group. So one of the glucose molecules will give up the entire hydroxyl, and one of them will give up just the H off of the hydroxyl. So we're just going to do it like this. Okay, and this is how CXC will also do it. So you'll have your two glucose molecules. One is giving up OH and one is giving up H to make water. And that means that this X now has a free hand to bond to this O that now has a free hand. And this is how it's going to look. It's just going to be O when we have glucose or polysaccharide bonding together. And this linkage, just an O by itself, is called an ether linkage. Okay, so this is going to be starch. A bunch of glucose together, we've got starch. And it's the ether linkage. Let's just go through all our linkages one more time, and then we're going to try and match which polymer makes what linkage or has what linkage. So it'll help us to learn how to identify our linkages. So the linkages that we know are, we have an alkane linkage, which will just be single bonds. We have an ester linkage, which is C double bond O to another O. And we have an amide linkage, which is C double bond O to an N and then an H. So your amide linkage is the only one with nitrogen in there. And if it's on a protein, we can also call it a peptide linkage. And then your ether linkage, which is from your polysaccharides, that just has the O alone. Oh, I just told you the answer, but let's just still go through it. So plastics or polyalkenes are all made from addition polymerization. And the linkage that forms is going to be your alkane linkage, okay? And then polysaccharides, we know, are going to be formed, well, everything else is going to be condensation, really. Condensation reactions, right? Which means they're going to make a polymer plus something else. That something else is water that they gave up, right? Now, polysaccharides, that's your glucose. Bonding together, you're going to make an ether linkage. That's just the O. Nylon, we know, has an amide. It's a polyamide, so it'll have an amide linkage. Polyester has the ester linkage, which there's a hint in the name. And then proteins are made from amino acids, so they also have an amide linkage, which we can sometimes call a peptide linkage. All right, that's pretty much everything about organic chemistry now. And now we're just going to do some CSEC past paper questions just to recap. Question 1. Polyethylene is manufactured in Trinidad and is used extensively throughout the Caribbean. Define the term polymer. So that's pretty easy for us. We know a polymer is a macromolecule or a large molecule, whatever you want to say, that's made by forming a long chain of monomers or linking together many monomers into a chain. So a macromolecule made by joining many monomers together in a chain, something like that. You don't really even have to say in a chain because you already got the point so far. All right, identify the type of polymerization that is used in the manufacture of polyethylene. So already we know this is many ethynes, that's an alkene, so it's a polyalkene, which means it's a plastic, which means it's addition polymerization. That's our polyalkenes. State 2 uses of polyethylene. So polyethylene, that's our plastic bags. That's the packages for snacks. That's cling wrap. I know it said 2, but I'm just giving you all the options here. State the name of one other polymer. And just for fun, let's just try to name as many as we can think of. So we have polyethylene already. So it said other. You could say polypropene, which is used to make rope. You got polytetrafluoroethene, or PTFE, which is our non-stick materials. We've got polystyrene, which is our styrofoam, and we've got polychloroethene, which is our PVC pipes. You could also say polymers that are not polyalkenes. We could do polyester, we could do nylon, we could do proteins, and we can do polysaccharides, right? Or we could even list the actual polysaccharides. We could say starch, we could say glycogen, we could say cellulose. So you have all these options to get that point. Next question. Polymerization is an important industrial process used in the manufacturing of many useful materials. Distinguish between addition polymerization and condensation polymerization. So I'm just going to use like arrows so we can distinguish, just to make this quick. So in addition polymerization, we already know one thing. The monomers are identical, or they use the same monomers, and they're alkenes. So that's something you could say. Also, it only makes one product, and that one product is the polymer, right? Whereas in condensation polymerization, the monomers are different, and it makes two products. It makes the polymer plus water, because remember, they give up water to make this polymer. Next part. So figure 2 illustrates the formation of a polymer, and they gave us figure 2. State the type of polymerization represented in figure 2. So if we look at our differences, we know that if the monomers are identical, then it's addition. But if the monomers are different, it's condensation. So we look at what they're joining together. Those look like two different things to me. This one has acids, this one has amines. So that's already a sign that it's condensation. It's two different monomers. So it's one type of monomer, one product, two different monomers, two products. So now you have two different monomers, and we also have two products. So that could have been the way that you chose to determine that it was condensation. We have two products, one being water. So we know it's condensation for this one. I gave an explanation for your choice, and I pretty much just showed you the explanations that you could say. You could say two different monomers or two products made, right? Those are your explanation why you chose that. There is a part C to that question. So part C says, identify one use of each of the following types of polymers. So polyester, we already know, is clothes. When we say 100% polyester, it's 100% fake. Okay, let's not say fake. 100% synthetic or man-made. So we have clothes. And also polyester is used to make PET stuff, like, you know, those bottles, containers and stuff. When you see that little PET, that means polyester. Polyalkenes, this is really vague for CXC to say. So you have any options of any plastic. You just need to say any plastics. So we could say plastic bags. You could say rope. You could say non-stick pans, you could say cling wrap, you could say PVC pipes, all the things, okay? Anything plastic related, styrofoam, right? And finally, define condensation polymerization. So condensation polymerization is linking together two different monomers by well, let's not say two, because it has to be like 50 or more, but let's say linking together different monomers by removing a water molecule from between them. Next question. Figure 3 shows compound A and compound B, which are from different homologous series. And we see compound A here, compound B. State the homologous series to which compound A belongs. So how you decide what homologous series a compound belongs is you just look at the functional group. This has a carboxyl functional group. So this is carboxylic acid. State the functional group of compound A. We just did that. So the functional group is C double bond OH. I'm not sure if they wanted you to, well, they said state, so let's just write carboxyl group, so you know the actual name of it. State the name of compound A. So we know it's a carboxylic acid, so it's going to be called something acid. We know that much. But we count how many carbons in a chain to figure out what's the actual name. So we have 1, 2, 3, 4 carbons. 4 is bute. So it's butanoic acid. Right. And state whether compound A will undergo a condensation reaction or addition polymerization reaction with alcohols. So compound A, it's a carboxylic acid, and they're saying it's going to react with an alcohol. So that's two different monomers. So we already know it's condensation. How else would we have known that it was a condensation polymerization? It's because really and truly the only monomers for addition polymerization are alkenes, and it's just not an alkene. So it must be condensation polymerization. Figure 5 shows the structures of an amino acid and propene. So we have the amino acid here and we have propene. Wait a minute. I'm pretty sure that was supposed to be an R here. But yes, an amino acid and propene. State the type of polymerization that the amino acid in figure 5 would undergo. So amino acid we know is condensation because all our natural polymers are made from condensation polymerization, right? Also, it has two different functional groups. We have, it's not an alkene. There's so many reasons that we could use, but condensation is the answer. State the general name for the type of polymer formed from the amino acid in figure 5. So anything with amine, we could say that it's a polyamide, but I really believe that because they said amino acid that they wanted you to say protein. Because you know the monomer amino acids will make proteins. If you couldn't remember that and you put polyamides, I think that shows that you know something, and I'm sure that they'll give you the mark. State 2 chemical tests that can be used to distinguish between propene and its polymer. So if we think about it, propene, that's an alkene, that means it's addition polymerization. Propene's polymer would have an alkane linkage. So it's basically you're differentiating between an alkene and an alkane. Right? Now, normally our first instinct would be by setting it on fire, right? Because alkanes burn with a clear blue flame, which is why they're used to make fuels. Whereas alkenes burn to give off a lot of soot, dark smoke, poisonous gases like carbon monoxide. But we cannot use that test when we're talking about the polymer of alkenes, because we said one of the problems with plastics is that when they burn, even though they have alkane linkages, they still burn with a dense smoke with poisonous gases. So we cannot use that test. So we have to think, what's another test that we can do? Our other test would be decolorizations. Remember, alkenes are reactive, and the alkane linkage would be less reactive. So if we mix an alkene with bromine, the bromine would get decolored. Okay, bromine test, then propene in this case would decolorize the bromine from brown to colorless. That would be one test, whereas the polyalkene would have alkane linkages, so it would become saturated. It would have only single bonds, and it would not do anything. It would not change the color. So that would be one way. You could add we could add bromine to both of them, and the one that decolorizes it must be the alkene. The one that does not decolorize it would be the plastic polyalkene, right? That has alkane linkages. And the second test would also be a decolorizing test. You could also use potassium manganate test, and the propene would decolorize. So the propene would decolorize the potassium manganate from purple to colorless, while the polymer would not change the color of the potassium manganate. So that would be your test. All right. And one more question and we'll be all done. There are several different types of polymers. For example, polyalkenes, polyesters, polysaccharides, and polyamides. Based on the following diagrams showing the partial structures of a polymer, deduce the type of polymer shown and the type of polymerization reaction that took place in each case. So first thing I want you to notice is that they've asked for two things in one question. So you want to really make sure that you read your questions properly to know what are they asking for. So they said they want the type of polymer shown and the type of polymerization reaction that took place. So for each one, we're going to have to put the polymer and the type of polymerization. All right, so let's look at what we got. So first things first, boom, let's look at this. We're looking at our linkage and we see it's an amide linkage. That already tells me it's condensation polymerization, because addition polymerization only makes alkane linkages, single bonds. So this second one, when I look at my bonds, I see it's all single bonds. So I know this is an addition polymerization. Now the types of polymers. So what polymer is this? Well, it has an amine group, so we know it's either... So one option here is to just say it's a polyamide, right? We can just say polyamides. But since we just did this entire video, and that's probably what they want us to put, because they give us some options right here, right? So polyamide, and we know that the addition reaction makes polyalkenes. So that's easy. But let's get even more specific, because we should know it after watching this video. Which polyamide is it protein or is it nylon? Let's look at this. If it was nylon, which is synthetic, it would have to have a double repeating pattern. So I should have seen CCNN, CCNN, but it is not a double repeating pattern. One molecule actually has both an N and a C on there. So that means this is actually a protein. Okay, and what about this? What polyalkene is this? So if we look at just one molecule of it, right, we see that you have 1, 2, 3 carbons. That means it's propene, and you have the CH3 group. Everything is telling us this is polypropene that's used to make ropes. Yes. Finally, draw the structure of the monomer used to form polymer CC. Well, we just figured it out. Once we saw the CH3, we should have known, to be honest, but whatever. So polypropene, we know it's going to be to a CH3 group, and then we're just filling the rest with H's. All right, and that's really it.